Okay, so this is where we left off at lab lecture. We had just mapped out 7 energy levels, and all the energies were given. And if you scroll down, we explored 2 different transitions. Remember, you could do this, run this code for any 2 transitions that you want. And one was an absorption, and the other was an emission. So if you're looking at emission, and you run the next block of code just to tabulate the data, 3 to 2 would be emission because the electron's falling down to a lower energy level. You're going to see that with the delta E being negative. And you can see the correlating frequency and wavelength for that particular emission of light. And we're seeing that the wavelength is 656. So if you come down here, we're seeing that that's going to be right here, which is red light. So that would be like the red line of light in the hydrogen emission spectrum. And there's a couple of links here, so you can explore some other animated visuals. But then we get into the lab part here, and you're going to run the first block of code, which allows you to enter your experimental wavelengths and color lines. And so you'll do that. Run the block again because it's not letting me. There we go. Enter them. So you know you're going to be seeing a blue line, red line, a teal line, a purple line. Those are out of order. You can enter them in any order you want. And then the corresponding wavelengths, I won't give anything away here. So I'm just going to do like whole numbers. And so you would enter your actual experimental data here. We just said red was 656. Going back up, 656. So we already know that that's what that one's going to end up being. And we'll base our calculations on that one. Teal is going to be somewhere around 480, and purple, again, you enter your own experimental values here. So I'm just entering rounded values. So we'll submit those. That will create the table, and then we're going to enter some code to start doing the calculations, starting with the wavelength in nanometers. We're essentially working backwards on this table, so we're starting with this, and we're going to convert that wavelength into a frequency, and that frequency into a delta E, and then ultimately use the Rydberg equation to solve for n initial. We already know that n final is 2 for the Balmer series, so that is our assumption that we're using here. And so for all of these visible parts of the electromagnetic spectrum, we would expect that the final energy value, and we understand that that's, at least for hydrogen, is true. And so we're really solving for n initial. So we stop at this first block of code right here, and we want to convert the wavelength in nanometers. Let's go with 656, red light, and we want to convert that into meters so that it's in a unit that will work for frequency, right? Because we need the speed of light. That's going to be given in meters, not nanometers. So the very first step is to convert to nanometers. Now we want to be able to go back through this code and do this with any number we want, not just 656. So that's the utility of doing this in code, or one of the advantages. Now Gemini is going to suggest some way to auto-complete this. We're going to define our function, unit conversion, and that's exactly what it says. Create a variable named wavelength. We did that. We named it, we created the variable, and it's set equal to 656 in this case. We're defining a function now named unit conversion. And remember, no spaces in these, so we need the underscore. And so this looks good. And we have the wavelength in parentheses. You can push tab if you want to accept that line of code, but I would modify this because what I want to do is define my function as unit conversion in nanometers, and then spit out that value, but in meters. So really all I want to do is return nanometers, okay, times, so asterisk, star, and 10, remember 2 stars is an exponential term, to the -9th. And this should be an N. Proofread. Okay, there we go. It looks good. I can run that. Now it doesn't like something. It doesn't like the indent. So this is the power of AI encoding, and so it's going to pick up on things and allow you to fix them. So you can say explain error. It doesn't like something about the way that that was entered, and it will tell you what that is, and then you can accept the change if that makes sense. An indent error, okay? So accept and run. And the little check mark here says that that code ran well. Now we're going to check it. This is just a try catch block here, so we don't have to change anything in here, just run it. And if everything makes sense up here and it's a wavelength that works for our program that we've created here, then it'll say you are correct. Okay, so just check to make sure that you're not way off with your data. And that makes sense because 656 nanometers would be 6.56 times 10 to the -7th meters.